This will be a very short lecture about tools that are at your disposal to do the attacks that we just described. I'll mostly go into detail about GDB, which is the GNU debugger, and which is incredibly helpful not only in debugging issues in your own software, but also in helping you exploit vulnerabilities in other people's software. Then we have a bunch of tools which we already discussed several times that are pretty simple, and I would recommend just looking at the man page, such as object dump and readelf. Linux also provides memory maps in the /proc followed by the process identifier /maps location. So this may help you understand the memory layout of a program. And then there are also commercial tools like IDA Pro and OllyDbg, which you might want to install and see if they work for you. So IDA Pro has, as far as I know, a free demo available, and it's actually known as one of the best programs for doing reverse engineering because it will help you much more than a simple program like object dump in understanding the structure of the code. For these programs, I'd recommend checking them out by yourself. For GDB, I will give a very short example to see how it works. So, this is the hello.c program, which we're going to debug. What happens here, we've seen it before, we pass a name to the hello function. The name comes from the attacker and contains an arbitrary number of characters, and using string copy, we store it in a buffer of only 16 characters. Obviously, if the name is too long, we're going to overflow the buffer. We have seen how you exploit a program like this. Let's see if we can use GDB to help us develop an exploit and to understand what is happening at runtime. So GDB is the GNU debugger. It's freely available. You can use it on pretty much any Unix-like system. It's using the debug features of the operating system, so if the operating system is limited in that sense. You're also limited. You can even use it when using Windows or Linux on top of Windows, because this just works like a regular Linux system. So it's very useful. And it has all sorts of features that help you debug the program, such as, for example, setting breakpoints, so executing the program up to a certain point, dumping variables or other memory contents, and also also lots of other features to run the program in certain ways or to dump information about the program in certain ways. Moreover, they can help you analyze core dumps, which the operating system creates after your program crashes. Unfortunately, if you're using Windows, as far as I'm aware, Windows does not offer core dumps when running Linux programs. Finally, the GDB is highly self-documenting, so it contains a built-in help command, which is very useful in finding the commands that you need to use, as well as how to use them. In the first example, let's see if we can debug using a core dump. Now, what is important here, well, again, we've used the no stack protector function because we're going to do a contiguous buffer overflow, which stack protectors prevent. So we'll see more about this later in the part about defenses. But what is especially important here is the -g flag. So the -g flag causes the compiler to include debug information, which, for example, tells GDB about the layout of the stack frames. This means that GDB will be able to help you, for example, tell you what are all the variables in the current functions and what their values are. So if you add -g when compiling and linking, you get better debugging with GDB. Also note that core dumps by default are disabled on many systems. You need to set ulimit -g unlimited, and in this case, if system policies allow it, the system will start creating core dumps whenever a program crashes. However, it is possible that there is some software installed, for example, by default on Ubuntu, that hijacks core dumps. If this is the case, I would recommend Googling for your particular system how to enable core dumps. On a system that is Linux out of the box, setting ulimit -g unlimited should work. So now we start the program with a long buffer. Now this buffer is just long enough to cause the program to crash. So what we see indeed, a segmentation fault, which means that there was an invalid memory access as well as the line core dumped. So if you don't see core dumped here, it may mean that you forgot about ulimit-unlimited, or that somehow your system's policies do not allow core dumps to be created. Now, the next operation is to call GDB and to tell it that you want to debug the hello program using the core file with the -c flag. Now, we see some interesting output and we type the command backtrace. Now, backtrace will give us a stack trace of the program at the time. So it's going to go through the different frame pointers and show for each current stack frame which function was executing at which point and what parameters were passed to it. Moreover, we can switch to a particular stack frame to get more information about it, such as local variables. However, in this case, we created a serious memory corruption, and the stack is already gone. So unfortunately, backtrace is not very useful right now. But we will see cases where it is very useful. So instead, let's try and see if we can reproduce the vulnerability in GDB itself. So now, rather than using a core dump, we're going to run the program inside GDB. To do this, we can use the --args argument, where we can specify both the name of the program and the parameters that we want to pass. So in this case, the parameter that we want to pass is again the input name that overflows the buffer. So this is on the first line. Now the GDB starts and we can set breakpoints. In this case, we will set a breakpoint on the hello function, where the buffer overflow actually occurs. Next, we run the program, and then it starts executing up to the point where the hello function is. Now see that this is super helpful. When we get there, GDB actually shows the parameters, including both the pointer of name and the value that is stored there. And it tells us which line we're currently at. So now we're ready to do the printf. We can do stuff like print local variables and parameters. So for example, if we want to know where buff is stored in memory, now this is useful, for example, if we want to figure out where it is in relationship to the return address, we can just print it. And it will provide us with the pointer that we're asking for, as well as its type. We can also print the current state of the program. For example, the info registers command will print the values stored in all the registers. In this case, I'm only printing some of the more relevant ones, right? So here, for example, we can see what the value of RBP and RSP is to get some idea of where the stack lives. Now, we can also dump memory that's not necessarily inside parameters or inside variables, but just give a pointer and show whatever is there in whatever format we prefer. Now, this is the x/ command, and it's followed by a command that specifies what to print and how to print it. In this case, the 8 specifies that we want to print 8 values. The G specifies that they should be giant values, which is GDB terminology for 8-byte values. And then the X means that we want to print it in hexadecimal. Use the built-in help of GDB to get information about more formats that you can print, because this is a super useful utility. And now we can just pass it a pointer, so a hexadecimal value of a pointer, and print the memory there. But we can also specify the name of a register, which is what we're doing here. So in this case, we're dumping the memory from the stack pointer onwards to see what lives there. Well, if we look at that point, we can find the return address at RBP plus 8. Right? So in the dump we saw the RBP ended in E2 E0. So this means that 8 bytes later we get the return address. And the value we see is very much consistent with what we would expect the return address to be in this case, depending on the other code pointers. So we managed to find the return address of the hello function in memory. Now, we also found the start of the buffer because we dumped the location of the buffer, right, using the print command. So now we can look what happens after we corrupt it. We trigger the vulnerability, but only after breaking on the string copy function. So we add a breakpoint, we continue execution, and then we get to the string copy function. Now we're not interested in debugging the string copy function itself, But what we want to do is we want to see the state of the program right after it executes. Now we have the finish command to do this. So it finishes the call to string copy, including any calls that string copy may make, and then returns to us when the call is done. Well, it tells us that it actually did this. It ran until the exit, and when it came back, it breaks again, and we can do more debugging. So now, for example, we can use the info locals commands, which dumps all the local variables, including the buffer that now contains only the letter A. It includes only what is within bounds of the buffer. So if we want to dump more, we have to use x/ again, which performs a full memory dump. And we can see clearly now that there is corruption here, including in the return address. Right? So the lowest order byte of the return address was now replaced with an A character. And the one just above was replaced with the null terminator, which explains why our program is crashing. So this gives us a lot of insight in what is happening. And if we're trying to perform an attack, but it's failing, memory dumps like this can make it much easier to debug why our attack is failing, which is why GDB is an incredibly helpful program whenever trying to exploit a vulnerability.